Most of chapter 6 was actually covered in the last section, which is the simplex method in general, knowing the algorithm, how it works, and how to use it. So this will hopefully be a slightly shorter video. 6.3 is the dual problem. So our goal here is to expand the class of linear programming problems that we can solve using the simplex method. And remember, our simplex method so far only applies to standard maximization problems of standard form. Well, now we want to ask about, what about minimization problems? What about finding the minimum value? And it turns out we can modify our, well, I don't want to say modify, but we can use our simplex method technique to solve these types of problems as well. So here I have a standard minimization problem in standard form, and it's the following. Minimize c equals 16x1 plus 9x2 plus 21x3, subject to x of 1 plus x of 2 plus 3x of 3 is bigger than or equal to 12. 2x of 1 plus x of 2 plus x of 3 is greater than or equal to 16, and again we have our non-negative constraints. So what makes this a standard minimization problem in standard form? Well, a few things. Once again, I'm asked to minimize, so it's a minimization question. I have my non-negative constraints that I always need on my variables. I have all of my inequalities are greater than or equals to. So when I'm working with minimization, I need greater than or equals to. Maximization, we have less than or equals to. And the last condition that we had on the standard maximization problems was that these values on the right-hand side, these constants, were non-negative. Turns out that's not what I need here. I need the coefficients. These coefficients of my variables in my objective function, I need those to be non-negative. Alright, so coefficients are greater than or equal to 0. So it's actually a condition on these coefficients and not these. And I'll show you why in just a second. Well, how are we going to solve this? Simplex method doesn't apply to problems of this form. So what am I going to do? Well, what I'm going to do is I'm going to form what's called the dual problem. And the way we're going to do this is I'm just going to build a coefficient matrix. Coefficient matrix that I'll call A. And the coefficient matrix is just going to be a matrix of the coefficients that we see in our system. It's not the same as the simplex tableau. Remember, there's a lot of work that goes into building the simplex tableau first. The coefficient matrix, I can just really quickly read this off. I've got coefficients of x1 are going to be 1, 2, and 16. So like the simplex tableau, I'm putting my inequalities first. So inequality 1 is row 1, inequality 2 is row 2, and at the very bottom here I'm going to put the objective function coefficients. So I've got 1, 2, and 16. Coefficients of x2, I've got 1, 1, 9. 1, 1, 9. Coefficients of x3, I've got 3, 1, and 21. I'm going to put my augmentation bar because now I'm at the right hand side of the equalities, or inequalities in this case. The constants here, I've got 12, 16, and for the objective function, this looks like two different numbers, 21. For the objective function, we always just put a 1 right here. With the simplex tableau, it's customary to put a dashed line separating your objective function from everything else. Here, in my coefficient matrix, I'm going to put a solid line. Again, they're just notational devices, but it indicates sort of what's going on, which pieces, which rows correspond to what. And what I'm going to do now is I've got my coefficient matrix A. What I'm going to do is build what's called the transpose of this matrix. So this is usually denoted as A superscript T, so A transpose. And forming the transpose of a matrix is actually really easy. All you have to do is interchange your rows and columns. So what do I mean by that? A transpose, the first row, we'll go rows. The first row of A transpose, is going to be the first column of A. So first column of A is 1, 2, 16. That's going to become my first row of A transpose. So 1, 2, 16. Second row of A transpose is the second column of A. So it's going to be 1, 1, 9. 1, 1, 9. Third row of A transpose is third column of A. 3, 1, 21. And I'm on my last row now, so I'll put a solid line there. And the fourth row of A transpose will be the fourth column of A. 12, 16, and 1. Alright, so building a transpose matrix isn't particularly hard. You just interchange the rows and columns. Alright, so rows of A transpose are columns of A. Still respecting the same order. First row is the first column, second row is the second column, and so on. Okay, so there's the transpose matrix. And how much space do I want? I'm going to point out one thing really quickly because I'm going to have to erase it. But notice that the constants here that I have, 16, 9, and 21, notice that that's the coefficients in this original objective function. Okay? Okay, so A transpose defines the dual maximization problem. And what I mean by that is it's still a coefficient matrix, it's just a coefficient matrix for a different problem. And if I want to give these variable names, how about y1 and y2? Well then what do I have? I've got an objective function down in the bottom. And the dual maximization problem is to maximize this. Maximize p equals 12y1 plus 16y2 subject to, we've got a whole bunch of inequalities here. I've got y1 plus 2y2 is less than or equal to 16. I've got y1 plus y2 is less than or equal to 9. And I've got 3y1 plus y2 is less than or equal to 21. And once again, my non-negative coefficients or constraints, y1, y2, y3 are all bigger than or equal to 0. So we used our original problem. Our original minimization problem, we built this coefficient matrix A. So we built the matrix of coefficients, pretty easy process there, just reading off the coefficients of the original problem. Using this sort of notation, solid lines separating the inequalities and the objective function. So we built our matrix A, coefficient matrix A. We took the transpose, so we transposed it, interchanging all the rows and columns to get A transpose. And then we claim that this new transpose matrix defines a new problem. And it does. This is called the dual of the original problem. And it turns a minimization problem into a maximization problem. Where once again, this is the coefficient matrix for the dual problem. Where I've just called my variables y1 and y2 here. But if I know all my coefficients and I know what the objective function is, then we can write down the dual problem. Oh, and the point I was making about these being the coefficients of the original objective function, remember I need these to be positive to be in standard form. So that's why for minimization problems I need the coefficients of the original objective function, which were 16, 9, and 21, I need those to be non-negative for this to make sense. So this is the dual problem. Why do we care, right? Why would I care about this dual problem? It seems like it has no relationship to the original. Well, here's the relation. Really important fact. The dual problem has an optimal solution if and only if the original problem knows. Okay, so if I were to solve this dual problem, which I can do using the simplex method because it's a maximization problem in standard form, if I find an optimal solution for this, then I know the original minimization problem has an optimal solution. And moreover, if an optimal solution exists, then the optimal solution for the dual problem is the same as the original problem. So also, if an optimal solution exists, it's the same for both problems. So if I can find an optimal solution, a maximal value for P in this dual problem, that's the minimum value for C in the original problem. Alright, so if an optimal solution exists, then it is the same for both problems. So that's about 99% of everything new in this section. If I want to solve a minimization problem in standard form, I build the dual problem. And I do that by building the coefficient matrix, taking the transpose, and then writing down what the dual problem is. Once I have this fact here, this theorem here, tells me that I can go ahead and solve the dual problem. Because if I solve this, if I find maximum value for P, that gives me the minimum value for the original problem, the minimum value for C. So how do we solve this? Well, we use the simplex method. Let's see. Again, I have to do this dual problem stuff first because the simplex method only applies to maximization problems in standard form. Maximization. So how am I going to maximize this using the simplex method? Well, we have to build the initial system. So I've got y1 plus y2, plus 2y2 plus a slack variable. In the last section, we were calling it S1. For reasons that will come clear soon, once we get to the end of this problem, I'm not going to call my slack variable S1 here. I'm going to call it x1 equals 16. Alright, so hearkening back to the original variables x1, x2, and x3. Let me leave a little bit of space. What else do we have? We've got y1 plus y2 plus my next slack variable x2 is equal to 9. And I've got 3y1 plus y2 plus slack variable x3 is equal to 21. And I need to move everything to the left-hand side now in my objective function. I've got minus 12y1 minus 16y2 plus p is equal to 0. Alright, so here's my initial simplex tableau. Looks pretty big. Alright, first column will be y1, coefficients of y1. 1, 1, 3 minus 12. 1, 1, 3 minus 12. Next we've got y2, 2, 1, 1 minus 16. Next column x1, 1, 0, 0, 0. Next column x2, 0, 1, 0, 0. Next column coefficients of x3, 0, 0, 1, 0. Next column coefficients of p, 0, 0, 0, 1. And then we've got our constants, 16, 9, 21, 0. There's the initial simplex tableau. I'm forgetting. I label this with my slack variables x1, x2, x3, and p. and we separate here with a dashed line. All right, there's my initial simplex tableau for this standard maximization problem. Now what do? Well, we go through the simplex method. So I look at my bottom row here, I choose the biggest negative value, the most negative value, the one furthest away from 0, which is minus 16. This is my pivot column. And I look at these numbers and I divide them into the constant for their corresponding row, and I choose the smallest one. So I'm not going to write them down because I'm running out of space here, but 16 over 2 is 8, 9 over 1 is 9, 21 over 1 is 21. The smallest value we found was 8, right? 16 over 2. So here is my pivot row, and that means 2 is my pivot column. I've also got my entering variable y2, my exiting variable x1. So what do? Well, first thing we do is I want to rescale this entry to a 1. So we're going to do 1/2 of row 1 becomes our new row 1. This should be a fairly straightforward process, hopefully. 1/2 of row 1. I've got 1/2, 1, 1/2, 0, 0, 0. And 16 over 2 is 8. Then everything else is the same. I'm going to be careful here not to make any copying errors. 1, 1, 0, 1, 0, 0, 9. 3, 1, 0, 0, 1, 0, 21. And minus 12, minus 16, 0, 0, 0, 1, 0. Cool. Now we have a bunch of row operations to do. All right, this was my pivot. I need to use that to zero out everything below it. So, a whole bunch of row operations. We're going to do row 2 minus row 1 becomes our new row 2. We're going to do row 3 minus row 1 becomes our new row 3. And to row 4, we're going to add 16 times row 1 to become our new row 4. So row 1, we'll copy this down really quickly. 1/2, 1, 1/2, 0, 0, 0, and 8. And now we've got row 2 minus row 1. All right, 1 minus 1/2 is 1/2. 1 minus 1 is 0. 0 minus 1/2 is minus 1/2. 1 minus 0 is 1. 0, 0, 9 minus 8 is 1. That one wasn't so bad. We've got row 3 minus row 1. 3 minus 1/2. That's 6 halves minus 1/2 is 5 halves. 1 minus 1 is 0, just like I wanted. 0 minus 1/2 is minus 1/2. 0 minus 0 is 0. 1 minus 0 is 1. 0 minus 0 is 0. 21 minus 8 is 13. And now the row operation with slightly bigger numbers, so we'll be careful here. Minus 12 plus 16 times 1/2. So minus 12 plus 8 is minus 4. Minus 16 plus 16 is 0 like I wanted. Then we've got 0 plus 16 times 1/2. 0 plus 8 is 8. 0, 0, 1. And then I've got 0 plus 16 times 8, 16 times 8, 10 times 16 is 160, minus 32 should be 128. Okay, there's our pivot operation done. One more thing to do though. Let's relabel our columns, y1, y2, x1, x2, x3, and p. And remember, if this is my pivot here, then this variable that I haven't labeled, but it was x1, x2, and x3, that's my exiting variable. So y2 is the entering variable, x1 is the exiting, so I'm going to put y2 here, x2, x3, and p. Cool. Now we do it all again. What's my most negative number? Minus 4, it's the only one. This is my pivot column. And I probably should write these down this time. I have enough space, so let's do it. I have to decide where my pivot entry is, which row. We've got 8 divided by 1/2. That's the same as 8 times 2 is 16. I've got 1 divided by 1/2. That's the same as 1 times 2 is 2. That's a pretty small number. And then I've got 13 divided by 5/2. That's 13 times 2 over 5. That's 26/5, which is bigger than 2, definitely. It's in fact a little bit bigger than 5, but it's bigger than 2. So this is my smallest among these. So this is my pivot row, meaning this guy is my pivot entry. So we'll go through the same process. First thing I want to do is rescale this to a 1. So multiply this whole row by 2. We'll just, I guess, continue above here. So we're going to do row 2, or 2 times row 2 becomes our new row 2. Copy down row 1, 1/2, 1, 1/2, 0, 0, 0, and 8. Scale this by 2 becomes 1, 0, minus 1, 2, 0, 0, 2. And then we're just copying everything else again. 5/2, 0, minus 1/2, 0, 1, 0, 13. And minus 4, 0, 8, 0, 0, 1, 128. I will keep track again that there's my pivot entry. And how about we keep track of the facts, because I don't want to lose these. I don't have to rewrite out the coefficients, those never change up top, or the variables up top, but I should keep track of my exiting variables. So x2 is going to get replaced by y1 when I finish this process. Okay, so now we have to zero out everything in this column. We're going to do row 1 minus 1/2 of row 2 becomes our new row 1. We're going to do row 3 minus 5/2 of row 2 becomes our new row 3, to put a 0 here. And we're going to do row 4 plus 4 times row 2 becomes our new row 4. Let's just copy down row 2 again. 1, 0, minus 1, 2, 0, 0, and 2. Okay, row 1 minus 1/2 of row 2. Row 1, 1/2, minus 1/2 times 1 is 0, just like I wanted. 1 minus 1/2 times 0 is 1. 1/2 minus 1/2, so 1/2 plus 1/2 is 1. 0 minus 1/2 times 2 is 0 minus 1 is minus 1. 0 minus 0 is 0. 0 minus 0 is 0. 8 minus 1/2 times 2, so 8 minus 1 is 7. And yeah, we'll keep going. Row 3 minus 5/2 times row 2. 5/2 minus 5/2 times 1 is 0, just like I wanted. 0 minus 0, that doesn't change. Minus 1/2 minus minus 5/2. So that's minus 1/2 plus 5/2 is 4/2, or just 2. 0 minus 5/2 of 2. 5/2 times 2 is 5, so this is 0 minus 5 is minus 5. 1 minus 0 is 0, or sorry, 1 minus 0 is 1. 0 minus 0 is 0. And 13 minus 5/2 times 2, again 5/2 times 2 is 5, so this is 13 minus 5 is 8. Last but not least, minus 4 plus 4, 0, just like I wanted. 0 plus 0, 0. 4 plus, or sorry, 8 plus minus 4 is positive 4. 0 plus 4 times 2, 0 plus 8 is 8. 0 plus 0 is 0. 1 plus 4 times 0 is 1. And last but not least, 128 plus 4 times 2, 128 plus 8 is 136. So I've got y1, y2, x1, x2, x3, and p. We had y2 here, x2 is exiting, y1 is entering, so y1 and x3 and p. I have no negatives left at the bottom here, so we are done. We can read off the solution. And what does this tell me? This tells me I've got a maximum of p equals 136, and it occurs when y1 is 2 and y2 is 7. I also know something about the slack. I know the slack x3 would have to be 8 and the other ones are 0, but we've used the simplex method to maximize the dual problem. Not what I wanted to do though, right? Not really what I wanted to do. What I really wanted to do was solve the original minimization problem, which was find the minimum value of c. And here that big theorem comes into play. The maximum value of the dual problem is the same as the minimum value of the original problem. So I don't really want this. The minimum value of c is also 136. And the really cool thing about this, and this is why I didn't call my slack variables S1, S2, and S3, I called them X1, X2, and X3, is because this, this matrix here, this table, actually tells me what values for X1, X2, and X3 give me this minimum. So it's when X1 equals something, X2 equals, X3 equals, and it turns out that it's the numbers here, the numbers at the bottom. So it's when x1 equals 4, when x2 equals 8, and when x3 equals 0. So really nifty that there's actually contained in this table these numbers that we haven't really looked at much in the past tell us something about the original problem, and it tells us when we attain this minimum is when x1, x2, and x3 attain these values corresponding to their columns, assuming I give them the same name as the slack variables would. So our last video ended up being pretty long because these simplex method problems take a long time. So I won't do another one. This is the only example we'll do. If you want to see more, again, there's a whole bunch in the text, but there's only one new thing in the section, which is if you want to solve a minimization problem, build the dual problem. build the dual problem, which is a maximization problem. Right? And the way you do that is you build your coefficient matrix and you take the transpose, and you build the dual problem that way. And you go ahead and solve it using the simplex method the same way as always. But when you get to the end, it's these entries here that correspond to your slack variables. These entries in the slack variable columns actually tell you how to attain that minimum value, right? So the maximum value for the maximization problem is the same as the minimum value for the minimization problem, but you can also figure out where that occurs by looking at the slack variables that you've called x1, x2, and x3 to remind you of the fact that these slack variables correspond to the original variables. So we'll stop here. Thanks.